Hello, everyone. Welcome to week 2 of distance learning in IB chemistry. Today, I want to share with you really quickly a skill to help you determine the type of chemical bond that two atoms will make with each other. As a quick guideline, ionic compounds are made between a metal and a nonmetal. Covalent compounds between two nonmetals, and metallic compounds are between two metals. This technique I'm going to share with you has a little bit more of a quantitative emphasis to try to help you determine this kind of relationship. To understand why this works, we need to revisit electronegativity. As we've learned in the past, electronegativity is something that was developed by Linus Pauling, a Portland scientist, and it is defined as the power of an atom in a molecule to attract electrons to itself. A little bit more about Linus Pauling. I'm going to kind of skip ahead a little bit. He developed a scale in 1932 that ranked elements based on their ability to attract electrons. It basically ranges from about 0 to about 4. These numbers here are unitless, and they're often depicted by the Greek letter chi, which kind of looks like an X. I'll be demonstrating the use of that in a little bit. So in general, think of the system of electronegativity as like a tug of war between two atoms. The greater the ability to attract electrons, the greater the electronegativity. And the one that has a greater electronegativity in a pair will usually be the more negative species, while the one that is lower electronegativity will be the more positive. There's the tug of war analogy for you. I'm going to skip ahead a little bit now on these slides, which I've also linked on the Google Classroom assignment, so you can review them. I'm going to skip ahead to how you can use electronegativity as a quantitative determinant of bond type. So hold with me one moment, please. So we skip ahead just a little bit. So this slide sort of describes kind of what we're going for here. If you take two elements and you determine the difference in electronegativity between them, you can sort of start to predict what type of bond they will have between each other. If they have a 0 difference in electronegativity, that kind of implies that the atoms are sharing the electrons between them totally completely, which makes them covalent, what we would call pure covalent. And there can be sort of an intermediate range where we define as anywhere between about 0.1 and 0.5 difference as the sharing is going on between the two elements, but not a complete sharing. We call those polar covalent molecules. And then the larger the difference, the more likely it's going to be ionic, where one atom will literally steal the electrons from the other atom and form ions, different sort of relationship with each other. So we get our covalent character decreasing as the difference between the two electronegativities increases. So this chart kind of can help you to see the difference between ionic and covalent compounds sort of on a spectrum of difference in electronegativity. I know the slide here says about 1.8. Generally, we use 1.7 as about the line between ionic and covalent compounds. It is not a clearly defined line, so we have to be careful with that and still rely on our quick guidelines of understanding of whether two elements are metals or nonmetals to help us really decide whether they're going to be ionic or covalent. As this way, it kind of gives us a range of values that might be able to be compared. So the rule of thumb between nonmetals and nonmetals and metals and nonmetals, it helps us to guide that. But the difference in electronegativity can be a supporting mechanism. So we're going to continue on, and I want to show you how you can distinguish not only between ionic and covalent compounds, but also metallic compounds as well. Because in actuality, if you look at the numbers of electronegativity, metals also have a very low difference in electronegativity between each other. So if they're forming a metallic bond, you have to be sure that you're not confusing it with a covalent bond, which also has a very low difference in electronegativity. To be able to distinguish between all three types of major bonding, you need a diagram and a skill using something called the Van Arkel-Ketelaar Triangle. In the triangle here, you can see that there's not only a spectrum of difference in electronegativity, which you see here on the y-axis, but a difference in, or a comparison of the average electronegativity between the two atoms, which is listed on the x-axis here. And then based on those two quantities together, you can categorize any pair of elements as being metallic, ionic, polar covalent, or covalent. What you can kind of see for metallic compounds is they have a very low difference in electronegativity, but their average electronegativity is low, which just sort of implies that both elements in the compound have a low electronegativity, which is characteristic of metals. So it sort of makes sense that metals and metals would go kind of in that region of the triangle. Covalent compounds, on the other hand, have larger electronegativities, so their averages would be likely higher, but they also have low differences because they are similar to each other. So the more similar they are, the more the bottom of the triangle is going to be present, but the higher the average, the more likely to be covalent. And you can sort of see the ionic situation is moderate average electronegativity, but larger differences. And then polar covalent is kind of like a combination of the covalent and ionic characters, sort of in the middle of those two. One of the skills that I will want you all to be able to do is to take any given pair of elements and calculate their difference in electronegativity, as you can see here with the chi symbol that I mentioned, as well as their average electronegativity, as you can see down here, and be able to place them in the triangle appropriately and define their bonding type. I'm going to go through a quick example of how to do that using an annotated image of the same image here. And you're going to be asked to do something very similar in your assignment for this week. So let me bring up my annotated image, and I'll show you how you can determine the bond type for something as simple as sodium chloride. So here you can see same image as before. Here I've taken the electronegativity values of the elements that are in sodium chloride, sodium and chlorine. I've just looked those up using my periodic table app on my phone, and I plug them into the two formulas. The difference in electronegativity between sodium, whose is 3, and chlorine, or chlorine's is 3 and sodium's is 0.9, is 2.1. So it's a fairly large difference, which you can plot roughly around here on the triangle. And then the average electronegativity I've calculated down below is about 1.95, which you can line up so right about here on the x-axis. So my placement of my point for sodium chloride is right about here, which is firmly in the ionic section. So both the electronegativity difference and the average electronegativity help me to see that the compound is designed as ionic. So that's how you're going to do one of the activities for your assignment this week. Hope you all have best of luck with it, and I will look forward to seeing you during our office hours if you have any